Alright, so in this video I'm gonna be explaining another important article with the title Information Theoretic Regularization for Multi-Source Domain Adaptation. This paper in 2021. Adversarial learning strategy has demonstrated remarkable performance in dealing with single-source domain adaptation problems, and it has recently been applied to multi-source problems. Although most existing MDA strategies rely on a multiple domain discriminator setting, its effect on the latent space has been poorly understood. Here we adopt an information theoretic approach to identify and resolve the potential adverse effect of the multiple domain discriminators on multi-source domain adaptation. Disintegration of domain discriminative information, limited computational scalability, and a large variance in the gradient of the loss during training. We examine the above issues by situating adversarial domain adaptation in the context of information regularization. This also provides a theoretical justification for a single and a unified domain discriminator. Based on this idea, we implement a novel neural architecture called multi-source information regularized adaptation networks. Large-scale experiments demonstrate that this model, despite its structural simplicity, reliably and significantly outperforms other state-of-the-art methods. We first introduced a notation. We have n number of source domains, and we have access to just the samples of the target, not their labels. So let hypothesis class H be a set of binary classifiers. Then for the given domain distribution, we can have, this is the true risk, we can have an upper bound on the true risk, because the risk of the target could be upper bounded by risk of the source and the distance between the source and the target. And the distance between the source and the target could be written as a supremum of the difference between the expectation of indicator of hx is 1 and indicator of hx is 1 when it is from target. So in their lemma, they say that this distance between the source and the target could be written as this equation. So a domain classifier can be used to compute the empirical edge divergence. One can obtain the ideal encoder classifier and classifier minimizing the upper bound by solving this one. So it is enough for us, because we know the upper bound, it is enough for us to just minimize the upper bound. And the empirical, the risk for the source can be written like this. So let P be the distribution of Z, where Z is in Z. Let H be a domain discriminator, where Z is the feature space, and V is a set of domain labels. So from feature space, for each element, we want to say that it belongs to which domain. So this is our domain classifier. Now that you have this domain classifier, this is the then I is like maximizing P of V, expectation of log of H, and plus H of V. So M is the number of total representation samples. I is the sample index. V sub I is the corresponding domain label. So for binary classification with just one source and one target that are equal size, we have this information regularized minimax problem. Now they talk in this section that what is the advantage over other MDA methods, other multi-source domain adaptation methods, because they are using information theoretic approach. Then they say that the relationship between 3 and 6 provides us a theoretical insight to the problem of minimizing mutual information between latent representation and the domain label is closely related to minimizing the edge divergence using the adversarial learning scheme. This relationship clearly underlines the significance of information regularization for multi-source domain adaptation. Compared to existing MDA approaches, which inevitably distribute domain discriminative knowledge over n different domain classifiers, the above objective function that we discussed, the above objective function enables us to seamlessly integrate such information with a single domain classifier H. Then they talk about the variance of the gradient, because using a single domain discriminator can also helps reduce the variance of the gradient. Large variances in the stochastic gradient slow down the convergence, which leads to poor performance. I sometimes use a clip in my PyTorch code that if it is gradient more than 5, it clips. But that way, it's very unnatural. Here is interesting when they are talking about their approach. So they analyze the variance of stochastic gradients of existing, we analyze the variances of stochastic gradients of existing optimization constraints. That is interesting. By excluding the weighted source combination strategy, we can approximately express the optimization constraint of existing adversarial methods as sum of the information constraints. So the sum of I and H. And this U sub K here is just the case domain label. So given M samples with M representing number of samples per domain, we have N domains, and per domain we have M, so total sample is M. An empirical version of 7 is 9. This is an empirical version of that. Do you see how everything is the same? Instead of this one, what is the empirical? Just summation. Just like if we have true risk, we have empirical risk. And then for the sake of simplicity, we make simplifying assumption that all variants are approximately the same for all K, and so are the covariance for all pairs. They can write the variance as a variance of individual and the covariance between each of these two. In other words, the covariance term may dominate the variance of the gradients as the number of domain increases. So this term became more significant. Let I sub m be the shorthand for maximization term. Then the variance of 5 is given by this. It implies that our framework can significantly improve the stability of stochastic gradient optimization compared to existing approaches, especially when the model is deemed to learn from many domains. Situating domain adaptation in the context of information bottleneck theory. I have a set of videos about this information bottleneck. I have a playlist about it. The information bottleneck in deep learning, something like this. So if you watch that, then you will understand the importance of this information bottleneck. This is the proposed neural architecture for multi-source domain adaptation. Multi-source information regularized adaptation network. Their model is called MIAN. Multi-source and target domain input data, for example, domain S sub I, S sub J, are fed into the encoder. Now that they have their encoder, they have we denote the arbitrary source domains as S sub I, S sub J. The domain discriminator is doing the work, outputs a logit vector like this logit vector where each dimension corresponds to each domain. For example, it says that the second domain is chosen. But they don't have any adversarial thing like the GAN approach. But they're just regularizing the mutual information between Z and V. To estimate the empirical mutual information, the domain classifier should be trained to minimax softmax cross entropy. So we slightly modify the softmax cross entropy. We modify this into multiple binary cross entropy. Specifically, we explicitly minimize the conditional probability of the remaining domains, accepting the true worth V's domain, where the objective function for the encoder is to maximize this objective. Here we show that this objective, is closely related to optimizing an average of pairwise combined domain discrepancy between given domain and a mixture of others. So we can define the edge divergence as the edge divergence between D sub V and D sub VC complement, and an average. So assume that the sample of size M does the domain label, then this is the empirical edge divergence. So when we say I of H of V is equal to Z, it means it corresponds to the Vth value. Corresponds to V's value of n plus 1 dimensional one-hot classification vector. Now you see the comparison of existing and proposed multi-source domain adaptation. In A, which is existing, it shows the existing multiple discriminator-based methods align each pairwise source and target domain, but may fail due to a disintegration of domain discriminative knowledge. It also may suffer from unstable optimization and lack of resource efficiency. But in B, our proposed model mitigates suggested problems by unifying domain discriminators. And this is for accuracy on digits 5 dataset.